Now calling Emily Lewis. She will present on the subject of single failure criteria for structure. So to the people standing on the side of the room, there is some free seats on this part of the meeting room if you want to come.
Good morning, everybody. My name is Emily Lewis, and I'm a structures expert in the VTOL department. So I will present to you the interpretation of the single failure criteria for structure, which is part C of the Design and Construction Principles requirement 2250 of the VTOL special condition. So the AMC and the guidance material for this subparagraph has been developed by my colleague Laurent Pinsard, who is senior structures expert for VTOL. He also prepared the technical content of this presentation. So the aim of the presentation is to give an overview of the requirement and the guidance material, and to explain EASA's interpretation and expectation to meet this very challenging requirement. So I'll start with a general introduction to the requirement itself and the reason behind it, and I'll then introduce the AMC material, giving an overview of the process in order to show compliance to the requirement. The AMC material is split into two parts. Part A, which is the main part to show compliance to the requirement, which includes a safety assessment. I will also explain Part B, which asks for an extremely improbable demonstration using compensating factors and provisions. And I'll also try and clarify when Part B can be used. And I'll finish with a concluding summary. So as a reminder of the requirement, for category enhanced only, a single failure must not have a catastrophic effect upon the aircraft. Now, this failure is both at aircraft level and occupant level. So if a single failure is unsafe for all the occupants, but the aircraft survives, this, of course, is also a catastrophic failure. I also want to highlight that this requirement is a design requirement, and what we want to ensure is the aircraft is designed to be robust against single failures. We do accept that this is a very challenging requirement. It's a new requirement. It's not part of CS 23, 27, and 29. But the unique design of the VTOL aircraft make this objective achievable. So here I show a few examples of the VTOL designs that we covered under the special condition. And the key design concept I want to highlight is the use of multiple lift thrust units. So due to these multiple lift thrust units, these VTOL aircraft can be designed to be less sensitive to catastrophic failures because sufficient segregation and redundancies can be incorporated into the design. So this makes our key objective, no single failure leading to catastrophic, achievable. So as a reminder, the special condition is only applicable to aircraft with more than 2 lift thrust units that's used for takeoff. So the examples on the right-hand side are not covered by the special condition, as it's accepted as well that meeting this objective would be significantly challenging for these type of aircraft. So in other words, the enhanced VTOL configuration is unique compared to rotorcraft and aircraft. With the multiple lift thrust units, VTOL is less sensitive to catastrophic single failure, provided that sufficient segregation and redundancies are included in the design, the structure, the lift thrust units, and their installation. And this is our unique opportunity to make single failure not catastrophic achievable. So even with all the precautions we currently have with CS 27 and 29, unfortunately in service we still have catastrophic events from single failures. And this is our chance to design against it. So far I've been concentrating on the multiple lift thrust units. Clearly the airframe design is not a new concept compared to rotorcraft. But with the use and consideration of multi-load path and crack or damage arrest features, the single failure not catastrophic can also be achieved for the whole of the structure, including the airframe, control system, and lift thrust units. So now we'll move on to the AMC, the guidance material overview, and our interpretation. So on the first slide, I'll just give an overview, but I'll go into more detail on the subsequent slides. So the process starts with a safety assessment, and this is part A of the AMC. If the result, when you've considered all reasonable and conceivable failures, is that no single failure would lead to catastrophic consequences, the requirement is met and the objective is met. If this is not achieved, we will request redesign or reconfiguration. And this redesign or reconfiguration loop should be repeated until the objective is met. However, we do acknowledge in some cases this objective may not be possible to achieve. If the redesign options or reconfigure options are impractical, add excessive complexity, or add additional potentially catastrophic failure modes, we can move to Part B. But Part B will be accepted only on a very limited case-by-case basis. It must be discussed with EASA, agreed with EASA, and documented. Again, I'll give more information later in this presentation. So the safety assessment process is very standard. Firstly, all the parts to be considered must be identified together with their functions. A functional hazard assessment should identify all the catastrophic failure conditions, taking into account all the foreseeable operating conditions, such as temperature, altitude, vibration, operating limitations. Then an FMEA should consider all the reasonably anticipated failure modes, with the objective to show that no catastrophic consequence from a single failure. As a reminder, this is a design requirement, so the FHA and the FMEA should be performed during the conceptual and initial design phases of the system and structure, taking into account all potential failure modes so that the proper provisions or redesign can be made to eliminate the catastrophic failures or consequences. So to clarify what a catastrophic failure condition is for this case, for enhanced category only, catastrophic failures are those that would prevent continued safe flight and landing of the aircraft. Not only do you need to consider the residual strength of the remaining components, but you also need to consider other parameters such as flutter, controllability of the aircraft, the fatigue loading on the remaining components following load redistribution to ensure you can continue the flight and land, the resulting vibration levels, and also the functionality and performance of the aircraft following the failure. So what failures need to be considered? What are reasonable and conceivable failure modes? And I'll try to explain with a few examples. So if we take a typical multi-load path structure, for example, would be a tail boom of a rotorcraft with skin and stringers, for example. Should you consider failure of the complete section? Is that reasonable? Well, this depends. It depends on your design. If this is a single one-shot piece, all of the same material, with no arrest features, then this potentially could be a reasonable failure and should be included in your safety assessment. Or is there a conceivable single failure or of a structure or system near this which could cause complete section failure? Again, if this is the case, it needs to be included. We're not going to ask you for unreasonable failures. We're not going to ask you to design against a meteor strike or the part spontaneously disappearing. It's only reasonable failures. So if the complete section failure is not conceivable and reasonable in your design, then the analysis should cascade down to the next structural level, complete skin failure, or all the stringers failed. Again, if the skin is a single part without arrest features, complete skin failure is conceivable and must be considered. Is there a common single failure that could cause all the stringers to fail? Again, this depends on your design and your configuration. In the case of crack arrest features, maybe complete skin failure is not conceivable, and therefore we move down a level again, and only one skin section should be considered. Maybe the result of the previous analysis is that only one string of failure should be considered. For the skin, if we move further down the levels, if the complete skin section is not reasonable, we move down. If it's sandwiched, do you consider one skin, two skins, or the core? The same for the stringer. If complete stringer failure is not reasonable, we move down a level, one flange, the web, two phalanges. The failure analysis needs to be carried out at each level and cascaded down for consideration and classification. For each step, you need to determine is there a reasonable or conceivable failure mode, or justify why there isn't, and that failure mode shouldn't be considered in the safety assessment. Again, this is all very dependent on your individual design. However, it's a design requirement, and it is promoting the use of multi-load path and crack or damage arrest features to avoid single failures leading to catastrophic consequences. Another example is a wing section with either single spar, multi-spar, two spars. Again, each structural level should be considered. If the wing is single shot, has no arrest features, maybe the complete section is conceivable and should be included in the safety analysis. Otherwise, should the complete covers be considered, or the complete spar, or all the spars? Again, it depends on your design. Otherwise, the reasonable failure modes of partial or complete sections of these elements should be included. So again, this is a design requirement. It's promoting the use of multi-load path design and arrest features. And of course, multi-load path design is only successful with inspectability, detectability, and accessibility also by design. Otherwise, the catastrophic failure modes are not going to be avoided. So, returning to where we are in the AMC process. Once the safety assessment has been carried out, considering all the reasonable and conceivable failures at all levels of the design, if no single failure is identified, we can stop here. Compliance is shown, the requirement is met. Otherwise, redesign or reconfiguration is requested and should be repeated until no single failure leading to catastrophic consequences is achieved. So here's an example of a typical single load path component from a rotorcraft. It's a pitch control rod. It's a single element, single load path, possibly no demonstrated residual strength capability or fail-safe capability. Therefore, complete section failure is a conceivable failure and should be included in your safety assessment. This would lead to loss of function, loss of the rotorcraft, potentially catastrophic consequences. If this single load path design was in a VTOL covered by the special condition, we would ask for redesign or reconfiguration. Another example are wing fittings with a simple upper and lower lug with a single bolt at the top and the single bolt at the bottom. Potentially the lugs are from the same material, one piece, same batch. In this case, a lug or a bolt failure may not be unreasonable to consider. This would lead to loss of function, loss of the wing, potentially catastrophic consequences, and therefore, if this was included in a design for eVTOL, again we'd ask for redesign or reconfiguration. So what type of redesign would we look at, or should you be looking at? So continuing on with our wing fitting example, here's a single load path example. You have a single spar with a single lug at the top on each side and a single lug at the bottom on each side, each with a single bolt. The failure of any part of this could be catastrophic, and therefore we ask for redesign. An example could be to have two separate spar parts, potentially from a different batch, and maybe with double lugs at the top and bottom. So we're starting to get into multi-load path design. We could even go even further. We have two webs, two independent spar caps at the top, two at the bottom, potentially with the double lugs. Great, we're all happy. This is multi-load path design, single failure is met. However, in this case, for the multi-load path, the complexity is increased, the part number's increased, and the weight is increased. Also, we acknowledge that the safety may not necessarily be increased due to the increased complexity of detectability of damages and the introduction of additional failure modes that could potentially be catastrophic. So when you look at your redesign, each of the options have to be carefully analysed and considered. Maybe the best solution for your design is somewhere between single load path and multi-load path examples here. Maybe any redesign would increase the failure modes and complexity to such an extent that the original design is the most robust against single failure. Here's another example of a control surface installation or a lift thrust installation with two attachment points. Each of the attachment points are simple lugs with single bolts. The failure of one attachment point is catastrophic, so we're going to ask for redesign. What could you consider? Well, a double bolt, for example, or double lugs, each with an independent load path, or a combination of the two. Alternatively, you could go for 3 lugs installation instead of 2. These could be the simple lugs as previous, or with the double pins and bolts and the double lugs. The best solution depends on the configuration of the aircraft. One solution may be preferable because it meets the requirement without introducing excessive design complexity and introducing new potentially catastrophic failure modes. It's very important in the redesign that you don't introduce new undetectable failure modes into your design. So the selection of the best solution also depends on inspectability and accessibility. It's also possible that the original solution, again, is the most robust against single failures. And this starts introducing the Part B of the AMC. So after completing the redesign and reconfiguration loops, it could be that single failure leading to catastrophic consequences is impractical, adds excessive design complexity, or introduces new potentially catastrophic failure modes. In this case, we move to Part B. However, this is very limited. It doesn't meet the objective of the requirement and must be considered on a case-by-case basis to be agreed with EASA and to be documented formally. This is very similar to what we currently do with CS 27 and 29 for damage tolerance, where damage tolerance is the key objective. However, if it is impractical within the limits of geometry, inspectability, and good design practice, supplemental procedures can be developed. So in this case, we're saying if within the limits of design complexity, inspectability, impracticality, you can use compensating provisions with the objective to demonstrate the single failure that would lead to the catastrophic consequence is extremely improbable, or the catastrophic result is extremely improbable. So what compensating provisions could you consider for Part B? What we'd ask for is a combination of compensating provisions, not just one. And here are a few examples. So we have design features, such as the use of higher safety factors, fatigue tolerance, including threat assessment and damage or flaw tolerance, specially assembly procedures or functional tests for the avoidance of assembly errors that could be critical, flight limitations to reduce the loading on your part, either to prevent the single failure in the first place or to reduce the loading on the other components so you can achieve the continued safe flight and landing. Inspections or checks to detect the failure mode or evidence of the conditions that would lead to the failure mode. Preventative maintenance to minimize the likelihood of occurrence of the failure mode, which could include replacement actions or verification of the serviceability of an item which may have a dormant failure mode, or installation of other safety devices. I want to highlight that the critical parts process CS2729 is not an acceptable compensating provision. As already highlighted at the beginning of the presentation, unfortunately, even with all the precautions we have from the CS27 and 29 requirements, including critical parts, we still have single failures leading to catastrophic consequences in service. So in conclusion, the no single failure leading to catastrophic consequences is achievable for VTOL thanks to the multiple lift thrust units and the possibility of having redundancy and segregation in the design. The key objective is to have a design that is robust against single failures. The AMC describes a process to show compliance, which starts with a safety assessment, considering all the reasonable and conceivable failures. Any catastrophic single failures need to be identified, and redesign or reconfiguration loops carried out. In the limited case that the objective cannot be met, Part B can be used, which requests a demonstration that the single failures leading to catastrophic consequences are extremely improbable using compensating provisions. And this is how to show compliance to 2250C, the design requirement. Compliance to the structural requirements doesn't end here. This does not exclude the need to consider the other requirements such as flutter, strength, protection of structure, etc. Thank you.